The Linrad transmit side is under development. This is in March 2015. This video will show the principles of the speech processor, which is the first stage of the transmit development for SSB mode. I have here two instances of Linrad running. One of them, let's click there and press U. You can see it's set up to receive from a Delta 44. This is connected to a soft rock ensemble. The sound card selected is the motherboard sound card, Realtek HD Audio. The other instance of Linrad is set up to receive the same signal, maybe not simultaneously, and it's also set to send the output to the same sound card. The transmit setup, I press V for the transmit side and then B for the sound card setup. And I have already set it up, and you can see that the transmitter output goes to the Delta 44 with port audio and ACO. That is good for latency. And then the microphone input is to the motherboard. The other instance of Linrad, if I press V and then B, is set up also to send the output to the Delta 44 ACO, but the input is from the Sound Blaster Live 24-bit external. That's a USB sound card. And this is to show the first step in the setup of the speech processor. To set up the speech processor, I press V and then C for setup in SSB mode. And here you can see there is a sine wave that is from a signal generator currently set at 1.3 kilohertz. And I can enable also the other instance of Linrad by pressing V and C, and it runs at the same time, and it is the same signal, but they use different sound cards. So this Linrad 2 uses the USB sound card, and the volume control is here, and if I increase, you can see it goes into saturation, and I put it just below saturation like that. The motherboard sound card, which goes for the upper version of Linrad, has its volume control here at the mic volume, so I turn the mic volume up, and you can see it goes into saturation here, so I turn it a little bit below. And here is an interesting thing. The first thing to set is a suitable gain on the hardware. That is the upper, I press the Alt key, click first and then Alt, and then the mouse becomes more visible. Here you can see saturation happens 6 decibels below full range, and I can turn on the signal generator to place it exactly at the point of saturation in the USB sound card, and then I have to turn down the volume here to get it just below saturation. So the motherboard sound card saturates 6 dB below full 16-bit range. We actually only have 15-bit here. But the USB sound card saturates here. So this is the first thing to observe when setting up the speech processor. One should set it for the normal voice from the microphone to be as loud as possible, but safely below saturation. We don't want to have saturation on the microphone signal because we want to do amplitude limiting on the RF signal and not on the audio. So after having shown the difference between these two sound cards, I will continue with only one of the instances of Linrad. So let's use the motherboard here. The first step in the signal processing is to apply an audio filter. I can press 5 to show the current filter. Well, I have to click first. 5. And I can change the filter here when the sound card, the first level here, when that is highlighted, it means I have access to some parameter settings. For example, I can change the slope, which is now 6 decibels per kilohertz. By pressing, let's see, F for slope. That is F. What? F, yes. And then I set the slope to -6 instead. And you see we have a different curve. Now this does not fit my voice so well, so I go back to the 6 dB slope. And I can also change the bass and treble by, let's say, T, and remove high frequencies a bit, let's say -10. And you can see it curves down a bit. T -25. And it goes down a little bit more. And I have on the bass -8 to bring the curve down a little bit here at very low frequencies. So I go back to the default settings. That is by R. I read from the disk. This is what I have. And this has to be adjusted for the individual voice. I can also change, of course, upper and lower cut-off frequencies. If I go back to 1, the raw data from the sound card, and tune the frequency, it is now 1.8 kilohertz. I tune downwards, and somewhere here the signal disappears. It is now about 50 hertz. And when I go upwards like this, you can see nothing happens. It's now 20 kilohertz. Because this is the microphone before the filter. I can press 2 to look at the spectrum. It's not so interesting because this is just a sine wave, but when I tune the frequency, you can see here That's the raw spectrum. Then I have the filtered spectrum by pressing 3. It is another scale, but it's now 2 kilohertz going upwards. Here it disappears at 2.8 kilohertz now. And I go down, and here is the lower limit, about 100 hertz. And you can see the level. Well, I can do like this, and then you can easily see that the signal is increasing. This represents the frequency response that I showed just before. I can also show the full spectrum of the filtered signal. That is 4 here. And note that the traces change color as I press in the different modes. So 4 is the same, but here it is wide. You can see that not all points are yellow. There are red points. They are below a cutoff level. So signals represented by red dots, they are not transmitted further in the signal path. And you can see the frequency is now 1.6 kilohertz. Here it's in the center of the passband at 1.4. When I go further down, the signal appears in the upper half of the spectrum. So here is the signal, now 850 hertz. The second harmonic is here, and the third harmonic is here. And the mechanisms applied here is going back and forth between the time domain and the frequency domain. So the filter is applied in the frequency domain, and then going back to the time domain, I press Q to get the next setup mode, which is the mute mode. Q. Here is the mode for setting the muting. The signal generator is at 830 hertz. I can press the attenuator knob on it. This is now 40 decibels less signal. And I can set the muting level to something about like that. It is now 15 dB, as you can see here. I don't remember exactly what the scale means, but I can press F to set the frequency domain threshold. F, and I make it 50. And you can see that the red points now are here at this level. Maybe it's seen better like that. And the overtones, they are not removed, but they are attenuated a bit. Let's make it F55. Sorry, F55. The buttons are not always 100% responsive here. It doesn't matter. It's just in the setup function for the speech processing. So this could be a reasonable setting. I can look at this in narrow by pressing 3. Here is what it looks like, and when I turn the frequency, you can see that if this now had been background noise from fans and other things, it could be a little bit better. I'm not sure how good it is to do this kind of muting in the frequency domain, but I have added it so one can make experiments with it. Then I can look in the time function and do muting there, but for that a sine wave is totally meaningless. So I will stop here and do some rearrangement on the signal generator. The signal generator now sends pulses at a repetition rate of 40 Hertz. And you can see on the microphone signal it's just a short rectangular pulse. The spectrum, if I press 2, I have to give it focus and then press 2. You can see when something happens we have an ugly spectrum. That's from the pulse. And here we have always some DC, a DC error. And if I look at the filtered spectrum, that is 3, you can see we have something. When the pulse is there in the time interval, when the oscilloscope displays, we have this curve, and then the frequency range, the frequency domain muting makes the output 0. And you can see muted says 68% or 62 maybe. So I press now Q to go for quiet or muting mode, and then I want to look at the time function. That is 6. It is muted in time as well as in frequency, and it has AGC, and it has also the clipper function enabled. So that is 6, and you can see the clipped function coming here, and the sampling rate now is different. So you can see if I press the gain button, that is the arrow, the up arrow, you can see that between these pulses there is silence. So now I apply some muting in the time domain, because the oscillations that last quite some time on both sides doesn't convey any good information if this had been a voice signal. So I press T and let's say 25. And T, and let's make it 40 then. Something like this, maybe even a little bit more aggressive, 50. Here, again, T, 55. Now the transmitter is switched off during much longer times. If I turn down the gain, you can see this is what it looks like. The purpose of turning off the transmitter between times when there is information is, in those times I want to listen. I want a very fast antenna switch, and I want to listen between syllables, or at least between words. I have now added a second audio generator to make a traditional two-tone test. One generator is on 430 Hz here, the other one on 1.8 kilohertz here. They are set for the same signal level after the filter. If I look at the filter, the microphone raw spectrum, that is number 2, you can see that there is a significant signal level difference, that the higher frequency is much lower here, and we see it in the time function also, that the low frequency is much stronger than the high frequency. I then look at the Q function where we have muting. It's not so obvious what this means because the center frequency at about 1.4 kilohertz, that is DC, and both of these frequencies have roughly the same offset from 0, but with opposite sign. Looking at the number 5 here. Sorry, I pressed the wrong button. This one. Now the AGC is applied. So if I turn the audio level up or down, you can see now level is minus 6.2. When I turn it down here, nothing happens until here. There is no AGC. You can see the AGC bar has gone away. But once the AGC bar becomes active, the level does not depend on the microphone level. So I set it at minus 6.2 like this. Then look at number 6, where there is not only AGC but also the clipper. That is 6. And I have to click here to give the focus, and then number 6. And you can see here is an ugly waveform. That is the clipped two-tone signal. And I can go to C, and there we have the same. And then look at the spectrum. Number 1 here is the clipped spectrum, the whole frequency range. And you can see the low frequency, the high frequency, intermodulation products above and below. So that is third order, fifth order, and there are of course overtones also. So this is a very ugly spectrum. Then I can apply a filter. That is number 3. Then only those two survive. And I can look at it in the narrow frequency mode. That's 4. Looking like this. It's more or less like the original signal. The time function before the clipper is applied, that is number 5. It looks like this. The crest factor here is 3.1. That is the ratio between the peak power and the RMS power. And that's what we expect for a two-tone signal. If I press 6, we get the clipped signal. And now the highlight is on this crest factor. It is 1.3 dB. And that is the peak power to RMS power of this ugly waveform. It is flat-topped, not I and Q independently. It is the sum of the squares of the red and the white curves that makes 1. If I go to the next level, that is P, and look at the filtered time function before ALC, that is 1. This looks like before, but there is some repeaking. 1.5 dB is the level now above 1, and that is not acceptable for the power amplifier. And the purpose of the ALC is to get the level back to the standard level. The ALC factor, that's number 3, that is the voltage by which the signal is modulated. I can set the time constant to 0 by pressing T and 0 like that. Then you can see that the gain is reduced at those points where the level is above 1. And the spectrum by applying this ALC function looks like number 4 here. And it looks ugly. It is one signal, the other signal, third order, fifth order, seventh order, intermodulation. The waveform we're adding on as a modulation contains high frequency. They form sidebands. So I have to change the ALC time constant, T, and I make it, let's say, only 0.5 seconds. And that suppresses all the high orders. We have a little bit of the third order intermodulation. This might be okay because the linearity of the amplifier is no better than this anyway. But the gain is extremely small. We are still very close to 3 dB. So the two-tone signal is not what we need to explain why the ALC is useful. I can have a look at the output signal. That is 5. And I have to enable the audio by pressing F3. And this is the transmit spectrum. And it looks nice. There is only one third order product down there, and it's really weak. I will need other waveforms to show what the purpose is of the ALC. The signal is now a sine wave at 1.3 kilohertz plus a pulse with a repetition frequency of 20 hertz. You can see it comes occasionally, travels through the oscilloscope on the screen. Here it comes. And this is the microphone in signal, the direct microphone signal. If I look at the interesting parts, it's where clipping is going on. The muted time function before the clipper is applied, that is number 5. It looks like this, and you can see the pulse is coming, and it's coming here again. The crest factor here is 1 point something, and the peak is 0. It means it is full power. But the important thing is the repeaking here. It's 1.3 dB. I go for P to look at the ALC here, and filtered time function before ALC. That's 1. It looks like this. And the ALC factor, that is number 3. it looks like this. Now with the time constant at 2.5 milliseconds, I start by making the time constant 0 to demonstrate what happens. That means t 0. And you can see the pulse is the varying number of peaks that go outside the power limitation. The spectrum with this ALC applied, number 4, looks like this. And what we see here is ALC induced splatter, something that is commonly happening in commercial transceivers. It broadens the signal by maybe 50 kilohertz or something like that. Here in Linrad I apply a suitable time constant. Look at the crest factor on the output. It is very small. It means the peak power is nearly full power. Sorry, the average power is very close to the peak power. I put the time constant to, let's say, 1 millisecond. Like that. And you can see that the splatter happens only very close in frequency. And of course that's related to the modulation. We are now modulating this waveform onto the signal and cannot generate sidebands that reach very far. The crest factor is still very good. I can, looking at the spectrum again, that is 4. Here comes the pulse. I make the time constant a little bit larger, t, and let's say 2.5. And I'm not so sure we made it much better. The modulation is by this signal now. And I can make the time constant much bigger, let's say t and 10 milliseconds. Here you can see artifacts from the algorithms in Linrad. The spectrum after this ALC looks like this. And I think we are within the passband here. I move the frequency, it's now 1.3 kilohertz. This is 2.2 kilohertz. So there is no reason to avoid unpleasant things within the passband. So I don't need this large time constant. Let's make it t and 0.5 milliseconds again. And then you can see the splatter down here. It is weak enough. And on a real voice signal, things become a little bit different. And I hope that this video has shown the mechanisms, what the processings are. And it's another story to set it up in an optimum fashion for a particular voice. And there is also another story to select sound cards and drive routines and parameters for optimum latency. We want this to be a fast system, work really in full duplex mode. And I hope it will be possible to run in SSB with a headset and listening to others while transmitting SSB. Because there are gaps when talking, like I'm doing now. there will be small gaps between words where I can hear whether the frequency is still free or not, or if somebody is trying to interrupt or so. That is rather interesting.